Continuity is one of the fundamental concepts of calculus. It's important because it defines a class of well-behaved functions. That is, functions that have other interesting properties. For example, a function that's continuous on a closed interval has to have a maximum value on that interval. We'll talk more about finding maximum and minimum values in a later lecture, but for now, knowing where the maximum and minimum values of a function are is extremely important in both science and physics applications. So, before we get involved in specific mathematical definitions, let's look at some specific examples that illustrate the kind of functions that we don't want to qualify as continuous. Now, in very high-level terms, okay, a continuous function is one that doesn't have any gaps or breaks or holes in it. The first graph here illustrates what we mean by a continuous function. You can think of a function as being continuous if you can trace its graph with a pencil without ever picking it up off the paper. Now, the remaining three graphs all have problems that will make them not continuous or discontinuous. The first graph has a split here at x equals 1. The second graph has this gap at x equals 1 where it jumps from one point to another. And the third graph has this hole at x equals 1. So our goal is going to be to come up with a definition of continuity that allows this first graph, that says this first graph is good, but that excludes all three of the others. So continuity, it can be defined in several different ways, depending on what you need to do or how technical you need to be. Now, the most straightforward definition of continuity is a heuristic one. That is, one that's based just on describing specific properties that a continuous function has to have. Then, any function that doesn't have even just one of those properties would be discontinuous. Now, a more technical and more complex definition is what's called the Epsilon-Delta Definition. This one is based on looking at smaller and smaller intervals around a point on the x-axis and looking at what the function is doing in the corresponding intervals on the y-axis. Now, the heuristic definition is easier to use when we're looking at specific functions, but it doesn't have the same power that the Epsilon-Delta definition has. We want to do things like make general statements, like the sum of two continuous functions is continuous. And finally, we have the topology definition. This is the most general of the three. The Epsilon-Delta definition only works for real-valued functions, functions whose inputs are real numbers and whose outputs are real numbers, where the topology-based definition works for functions whose domain and range can be any kind of set, not just sets of numbers. It's the most flexible of the three, but it's also generally the hardest of the three to work with. So in the next lectures, we're going to build up a heuristic definition of continuity, then see how we can apply it to specific functions.